Welcome back to ECE 442-542. Tonight, it is PM, I guess, now, but later tonight we will have a review session for exam number 1. The idea is to have it in this room. Hopefully we will not get kicked out. If we do, we'll go have it, I guess, underneath the underpass. Somebody was over playing the drums. We'll have to do our own drumming at 7 o'clock. Exam number 1 is on Wednesday, the next time we meet, and updated material is, the updated topics are listed on D2L. That was updated just a couple of hours ago or an hour ago. I'm noticing a few things that still need to be placed there. Today, let's quickly go over the process of exam number 1. If you've looked at any of the previous exams, it's basically on one of the front pages of that. I want to summarize the region of convergence, what the different possibilities are, and maybe show you what happens when you have more than 2 poles. I think that was one of the questions after class last time, is what happens to the region of convergence when you have 3 poles? The poles cannot live inside a region of convergence, and that means that they have to somehow be somewhere relative to the region of convergence. And hopefully that will be clear after today's class. All of this region of convergence discussion is because we want to make sure that we can find a unique little x of n, let's say, if somebody gives us a capital X of z. For the Z transform. We want to be able to find the inverse Z transform and to do that uniquely. A lot of times we will just assume, if it's not stated explicitly, that our region of convergence is outside all of our poles. And that then corresponds to a causal time domain sequence, little x of n. That could be stable, it could be unstable. And we'll show that today. Then we will move into some new material, which is discrete equivalence. How do we convert continuous time transfer functions into discrete time transfer functions? And there's really 2 main reasons for doing that. And we'll get into that maybe today's lecture. This is a digital controls class, meaning discrete. We have zeros and ones. So I have a 1 and a 0. What is allowed and what isn't allowed for the exam. What is allowed? 1 sheet of notes, front and back. So that's 1, 0, if you're keeping track in binary. Sorry. A transform table I now have put on D2L, and if you want a transform table, be sure and print that out and bring that with you. So you'll have 2 pages of notes. 1 is front and back. This one should just be the front, and it's coming from the Shams outline. You can also bring any calculator except for those that basically, well, they all are computers now, but don't bring a reasonable calculator, an 89, an Inspire, an 84, whatever you feel comfortable with, and something to write with. I don't want to be reading exams in blood. So bring something that you can write with. What's not allowed, you can't have a computer, a cell phone, textbooks. We don't have a textbook for this class, but there are textbooks out there that you could bring. Don't bring them, or don't put them on the desk. We don't have enough table space, basically. This classroom will probably be packed once everyone shows up for one lecture or an exam. And you can't bring your class notes. Whatever you can fit on that 1 piece of paper is what's allowed. Questions on the exam process? How many problems? I don't know. 4 or 5, probably. And they may have multiple parts. All right, let's get started with the material for today. And I would preface this by saying this is not on exam 1, but I don't want you to just tune me out. It's not on exam 1, but don't tune me out, okay? But this helps you understand what you're doing when you are taking Z transforms and finding maybe this region of convergence. Let's look at the region of convergence, and here I've illustrated it with 4 poles, but you can see that none of these poles lie inside the region of convergence. A couple are interior to the region of convergence, and a couple are outside of the region of convergence. And what I want to do then is try to talk about these different possibilities. Here, for this particular case, we can associate certain values of the little n time index with these associated pairs of poles, meaning we can associate, what do I want to start with? The poles larger or beyond the region of convergence. So associate the poles larger than the annular region. And I hope it's clear that I'm referring to as poles 1 and 2. Those are outside the annular region. Those then, if we have a mode associated with pole number 1 and a mode associated with pole number 2, those modes are raised to the nth power, and n now is negative. That's what I'm meaning by that in the generic structure. And this basically says that for these 2 poles, poles 1 and 2, the region of convergence is interior to those poles. So I'm saying it many different ways, but hopefully it is making sense. So our region of convergence is inside those 2 poles, poles 1 and 2. Or those 2 poles, 1 and 2, are outside the region of... See, that's what I get into trouble with. 3 and 4 are outside the region of convergence, but they're interior to... Do you see what I'm having trouble with, maybe with terminology? But I hope it's clear what I'm meaning. So here, the region of convergence is interior to the poles 1 and 2. We can also associate the poles that are smaller than the annular region. And that now corresponds to poles 3 and 4 with non-negative values of the time index. So now 3 and 4 are inside this annular region, is what I'm meaning by that. Or here, the region of convergence is exterior to poles 3 and 4, and because it's outside the poles, that now corresponds to these time indices n that are non-negative. Now, I didn't place any labeling on my real axis of z, which means that I could sort of make this anything I want in terms of its bounded or unbounded nature. But if the unit disk or the unit circle was living inside the region of convergence, then this particular set of poles would correspond to a bounded or stable waveform in the time domain. Let me try to word that. So if this region of convergence contains the set of points on the unit circle, or when z has a magnitude of 1 in the complex plane, if the region of convergence contains that ring, or the circle, then the time domain sequence, whatever we've labeled it to be, and this actually could be one-sided or two-sided. That time domain sequence is bounded, or maybe we will refer to that as a stable waveform, which if you looked at from the definition of the z-transform, if we looked at this definition, this sum from n equal minus infinity to infinity of f of n z to the minus 1, but if z is on the unit circle, we could say, well, let's just pick one point of z, which is 1, right there on the real line. Then we would have this sum. Since we have claimed that this is bounded for all values of z inside the unit circle, inside the region of convergence, and if our region of convergence contains the unit circle, then we could replace that z with anything in that region of convergence, and that sum would be bounded. Let's just pick one point right on the unit circle. Then we know that all of these time values, f of minus 2, f of minus 1, f of 0, plus f of 1, when summed together, since this is just the expansion with z raised to the minus 1, z raised to the minus n, z raised to the minus n is 1, and all of those go away, or basically all collapse to 1. This sum is bounded or finite. Or if you wanted to, you could just think of it as here is f of n, and now you have a well-behaved, either one-sided if we covered up one of these sides, or it could be two-sided. This is now our time index n. That's one way of trying to summarize this region of convergence. Yes? So the region of convergence, if it's really the region of the poles need to be inside the unit circle. So in this case, that's for a system. This now we're talking about a waveform. So we have two different things that could be transformed. We could transform signals, or we could have the z-transform of a system. A system, we like all of its poles inside the unit circle, and then it will be a bounded input, bounded output stable system. Here we're really just talking about a transform, and we want to know what would happen to its time, or its time domain sequence, little f of n. And in this case, if the unit circle is inside that region of convergence. And so if this pole, let's say, was less than 1 in magnitude, then the region of convergence would contain the unit circle. And that would then correspond to a bounded time domain waveform. Yes? So now, because this is a waveform, and this is now our region of convergence, this now is saying that these two poles, 1 and 2, correspond to an anti-causal time index, or indices that are negative. Which means if 1, let me go through another example, and hopefully this will be clear. But yes, 1 and 2 could be poles outside the unit circle, but they now correspond to negative time indices. So they're bigger than 1, but yet they're raised to a negative power. So they basically are in the denominator, and when you raise that to a bigger and bigger power, you're really just collapsing the contribution due to 1 and 2. And hopefully that will make sense as I go through one more sort of example that's a lot of different possibilities. Yes?
So if poles 1 and 2 were inside the unit circle, then this waveform would not be taken.
So the question was, if 1 and 2 are inside the unit circle, then this particular picture would correspond to unbounded waveforms. And we'll look at, hopefully we'll illustrate that with some of the possibilities that I want to go through now. Okay, so maybe we can address some of these questions with one more sort of iteration on this with different region of convergence possibilities. And now I will assign numerical values to the poles that I'm going to sketch. Let's see, and I'm trying to do this, I'm trying to color code this, and hopefully it will work. Meaning all the notes that I write for that region, I need to stay in green. I'm going to have multiple regions of convergence. And in this case, let me draw which color am I not using? Maybe red. So let me draw my poles in red. That pole is at 1/2. This one's at 3, and that one's at 4. So that's one possible region of convergence. It's interior to all the poles. Another region of convergence, which I'm going to illustrate, and I probably didn't give myself enough room, but you can, is now going to be between 1/2 and 3. So, and this one I will call region of convergence number 2. This one is region of convergence number 1. I'm sure you can read that. And then my last one is actually going to be beyond 4. And by definition, none of these poles can live inside a region of convergence. So hopefully that's clear from this sketch. So I have 3 different possible regions of convergence, and we'll talk about those 3 regions separately now and what they can correspond to. All right, so let's look at the first one, region of convergence number 1, which I've shaded in green. So I need to make sure I'm green. Kermit, for all you Sesame Street children. All right, region of convergence number 1. This region of convergence is actually interior to all the poles. And that means when I'm looking at the structure of the time domain waveform, all terms in the time domain structure are what? Causal or non-causal. My region of convergence is interior to all the poles. So now we have a 50-50 chance, right? These are now negative time indices. Now we can say that our structure, and let's just call all of these F sub n, but here I'll label it, well, let me say the structure of the waveform, and I'll call the waveform F sub 1 of n. I'm going to have a factor that I'm going to raise 1/2 to the n. I'm also going to have a mode that is 3 raised to the n, and I also have a 4 raised to the n. Those modes are in my time domain waveform F sub 1 of n. And that's actually going to be in all of my waveforms. But here, let me say I have an alpha 1, 1/2 to the n, plus an alpha 2, 3 to the n, plus an alpha sub 3, 4 to the n, and that n is a non-causal n. Those are negative values of n. Now, causality and boundedness of the time domain waveform are two separate notions or concepts. Now, I know that this is the structure of my waveform for that region of convergence. What can I say about the boundedness or unboundedness behavior of this waveform F sub 1 of n? Little n now is less than 1. I'm sorry, is less than 0. It's -1, -2, -3. What happens to 1/2? I'm raising it to a -1. That's now a 1 over 1/2. That's 2 raised to the 1. When I go to -2, -3, -4, values of n, now I'm basically squaring 2, cubing 2. What's happening to that term? It's going unbounded, isn't it? These two terms are well behaved. That's basically 1/3, 1/3 squared, 1/3 cubed, etc. when I have negative n's. This guy, though, is problematic. This is going to give us an unbounded behavior in the time domain. Now, could we have predicted that based on what we know about the region of convergence in the unit circle? If we drew a unit circle in here, which is at 1, j, -1, minus j, where is that relative to this green shaded region of convergence? Is the unit circle contained in that green shaded region? No. So we could have anticipated that that waveform is going to go unbounded. So for F sub 1 of n, Region of convergence number 1 does not contain the unit circle, and these two are consistent. We looked at the time domain waveform with n negative, and we looked and found that that was going unbounded, and that was consistent with this unit circle concept relative to the units, to the region of convergence. Is that clear? Any poles that are outside the region of convergence are going to be non-causal in their time domain behavior, the mode associated with that pole. I needed to scroll back up here to see what color I'm on next. Let's move on to region of convergence number 2, which is the black region. The green is now not shaded. It's just the black. And this one is now annular, the black region. So I have one pole that's inside that, or interior to the region of convergence, and two poles that are exterior to that region of convergence. Region of convergence number 2 is interior to poles 3 and 4, and exterior, well, maybe I should have said poles at 3 and 4, because I'm not circling these, am I? Sorry, I'm not taking notes in pen, am I? I apologize if you are. So if the region of convergence number 2 is interior to the poles at z equal 3 and z equal 4, and exterior to the pole at z equal 1/2. Now, what can we say about well, how does this region of convergence, how's that relate to the unit circle? Does it contain or not contain the unit circle? It contains the unit circle, and what can we conclude about the time domain waveform's behavior? It needs to be bounded, or it's a stable sequence. And what can you now write down? And I may ask this actually on exam number 1, is the structure of your waveform. And then you don't have to do formally the partial fraction expansion or find those coefficients. You can leave those undetermined, but you need to find their structure. So the structure of the waveform looks like what? What does it look like for n positive or non-negative? So we have 3 different modes, don't we? We have a 1/2 to the n, we have a 3 to the n, and we have a 4 to the n. And in this particular region of, or relative to this region of convergence, modes 3 and 4 are in the same location relative to the region of convergence. So we could add those two up. Read the mode associated to 1/2 is by itself, and what time values of n, non-negative or negative, are associated with the mode at 1/2. Oh, let me make this something else. Let me call this beta. Is that okay? 1/2 is raised to the n, and n is non-negative because that 1/2 is interior to the region of convergence. The other pieces are for negative indices, and now we have the 3 basically effectively downstairs and the 4 downstairs, and that, when we hit it with higher and higher powers, is going to collapse, and that's what we want to have happen. We've now seen that for this particular case, a two-sided, which is what f sub 2 of n represents, a two-sided stable sequence is what we ended up with, and the positive index sequence, or n non-negative, corresponds to a well-behaved or bounded sequence. And the negative index sequence for n negative, it too corresponds to a well-behaved or bounded sequence. Meaning, even though we have a two-sided waveform in the time domain, it could be corresponding to a bounded behavior. Yes? I'm sorry? Oh, does it matter which side the time index 0 is living in, positive or negative? I probably should have said, instead of the positive, I should have said non-negative index sequence. It's usually associated with the positive part of that time domain, or of that time axis, in 0 and positive. Was that your question? That's the convention. Now let's look at the last of these 3 region of convergence, ROC number 3. Region of convergence number 3 is external to all the poles, or it's lying beyond all the poles, or stated another way, the region of convergence expands in this case outward to infinity. So here you have to kind of watch how I'm modifying or how I'm using unbounded. Now this unbounded, this is now an unbounded region of convergence. I'm not talking about the time domain waveform just yet. Or this region of convergence contains all values of z out and including or approaching infinity. That's why it's unbounded. Now, if I have an unbounded region of convergence that contains infinity, what do I know about my time domain sequence? If I looked at the definition of the Z transform and I said, okay, I have f of at time -1, Z to the minus 1, what's that going to do? Now I have f at time instant -1 raised to the Z. But Z is now infinite. So that's forcing f of -1, f of -2, f of -3, all of those negative time indices to be 0. The unbounded region of convergence then, or the fact that it contains infinity, that now says that the sequence is a causal time domain sequence. That means that all of the f sub 3 of n's are 0 when n is less than 0. The time index is negative. And we can have non-zero f sub 3 of n for non-zero or for non-negative n. So f sub 3 of n can be non-zero for n non-negative. If we go back to this region, how is that region related to the unit circle? Is the unit circle contained in this blue region of convergence? No. So what do we know about the time domain behavior? It's not a bounded behavior, is it? So this one, however, region of convergence number 3 does not contain the unit circle, which says that we now have an unbounded or an unstable time sequence. And we can see that also if we look at the structure of the time domain waveform. F sub 3 of n is some constant, gamma 1, 1/2 to the n, plus gamma sub 2, 3 to the n, plus gamma sub 3, 4 to the n, and that's for non-negative values of n. This tells us that our waveform is causal. It's valid for non-negative values of n. But now if we raise 3 or 4 to higher and higher powers of n, those are going to go unbounded, aren't they? So even though this is causal, that really doesn't impact whether this sequence is well behaved or not. Let's see if we can make some observations from what we've been seeing. And you might want to even whistle to these observations. Signal causality and bounded time response behavior are two separate characteristics. We can look at those two behaviors separately. They're not connected. A signal can be causal, and how is the region of convergence related to the poles of a causal sequence? If I say I have a causal sequence, what do you now know automatically about the region of convergence? It's all outside of every pole, isn't it? So now we could say, okay, I have a signal that's causal. A signal can be causal. That says that the region of convergence is external to all poles. If it's causal, it's defined for n non-negative. And even though it's defined for n non-negative, the signal itself could be unbounded. And we just saw that in one of the examples. The signal being unbounded, that just means that we have one or more poles that are beyond z equal 1. And now if you had to come up with an example that might illustrate that, you could say, oh, I have h sub 1 of n equal to 5 to the n. I hope it's clear that that's unbounded, but this says that it's causal. But if I wanted to z-transform that signal, what would my region of convergence look like if it's causal? I have a pole at 5 corresponding to that mode 5. And my region of convergence is exterior to that pole. In order for the z-transform to converge or to give me a valid result. So the region of convergence being outside the poles allows the z-transform to exist, but it corresponds to an unstable time domain sequence. And we could look at the flip side of that. By that, now I'm saying a signal can be non-causal, which means it's defined for negative time indices. What do we know about the region of convergence if we have a non-causal signal? It's interior to all of the poles, isn't it? So this region of convergence is interior to the poles. And yet we could have this being an unbounded waveform. What would be an example of that? I now have a region of convergence that's interior to a pole, and that region of convergence needs to be what relative to the region or the unit circle?
The major that equals 1/2.
So now what I'm wanting, this is going to be a negative value, isn't it? So the one that I picked, it just has to be less than 1, doesn't it? As long as this value is less than 1, then when I raise it to negative powers, it's actually going to effectively be getting bigger as n marches off in the negative time direction. And that's going to give me an unbounded waveform, where this is now n less than 0. There's our non-causal. And this now says that we are unbounded because one or more poles are inside z equal 1. Here, in this example, I just had one pole, and it was inside the unit circle. Meaning now I would have at time -1, at time -2, at time -3, and this probably won't be to scale, but this value is now 4/3. The next one would be both of those two squared as a ratio, or 16/9. Then we do it again. We scale those by 4 and 3 respectively, or 64/27, and hopefully you can see that that's going bigger as time marches to negative, more negative and negative values. And the region of convergence here is interior to 3/4, which is why, or that's what it needs to be in order for our Z transform to converge in that infinite sum. These two examples that we just worked through showed that we could have a causal unbounded and we could have a non-causal unbounded, but the other two cases are also possible. Which are what? A causal sequence that is bounded or stable. Now I just have to have my modes or my poles inside the unit circle. Let's say 1/4 to the n, and it's causal. N is greater than or equal to 0. And what's the region of convergence look like here? I'll do the hard part. All right? So it's somewhere. 1/4 is either interior or outside that dashed line. If it's causal, what do we know that region of convergence needs to be? Outside. So now we know that the region of convergence is such that z, the magnitude of z, is bigger than 1/4. And we could also have the other case where we have a non-causal or a negative index sequence that is stable, and the one that I picked, now it needs to be bigger than 1. I just picked 6 for n less than 0. And what's the region of convergence for this? If it's non-causal, my region of convergence is interior to all of my poles. This is now in here. And my region of convergence is now less than 6, or the values of z are less than 6. Questions on region of convergence? Now do you have a better feel for that? Based on your region of convergence, now you can uniquely determine the inverse C transform, knowing what you know about the the region of convergence. So let's now talk about the inverse C transform. If we're inverse C transforming, in order to find a unique inverse, which by that I'm saying a unique x of n, we actually need two things. We need the transform, capital X of z, and the region of convergence. We need both of those. Let's look at an example. And now this should be trivial as far as finding these inverse C transforms. Suppose somebody gives you the transform capital X of z equaling z over z minus 1/4 factor and z minus 2 factor. Now, whether that corresponds to a bounded time domain waveform is going to depend on the region of convergence that we're told or that we're given or that's specified. if I said this was a causal sequence, where's the region of, if this corresponds to a causal time domain waveform, little x of n, what would the region of convergence be? It would be exterior to 2, wouldn't it? It would be 2 and beyond. To infinity and beyond, right? Where's Buzz when you need him? So now that's the region of convergence for a causal waveform. If it was anti-causal, now the region of convergence is inside 1/4. It has to be interior to all the poles, and if it's two-sided, then we know that the magnitude of z is living between 1/4 and 2. And that's now the region of convergence I want to specify. Let's answer some questions. I said that your problems on the exam might have multiple parts. Let's look at some questions that are multiple parts. And these you should be able to just do in your sleep. Okay, so the first question you might say, or ask yourself, the poles of x of z equal what? Those are positive, aren't they? Those are the values of z, the finite values of z, that cause that transform to explode, or the denominator to equal 0. What about another question? 2. And I've already answered this. Is x of n one-sided so I shouldn't have been talking so much, or two-sided? And what tells you that it's two-sided if I hadn't already told you that? What can you say about the region of convergence if somebody said you have a two-sided time domain waveform? Describe the shape of your region of convergence. It's annular, isn't it? It's a ring. It's not a solid region. That would be anti-causal. If it had a hole in the middle of it, but everywhere else it was present, that would be causal. The fact that it's annular says that it's two-sided. Question 2 then is x of n one-sided or two-sided? Because it's an annular region of convergence, it's two-sided. Do you see how much we're learning just by looking at this and not even doing any computations? What have we learned? We know where our modes are, where our poles are, so we know that, well, I better be quiet. 3. You walk into your boss's office and he says, I don't know, I've been scratching my head on this capital X of Z. What's X of N look like? What's the structure of the time domain sequence? And you can now, just by knowing 1, you can help him quit pulling out his hair, right? It has a mode of 1/4 to the n and 2 to the n. And you can actually provide more information than that. What do you know about the mode 1/4 to the n and that power of n? where is 1/4 relative to the region of, or where is the region of convergence relative to 1/4? It's exterior, isn't it? So that means that this guy must be associated with causal or non-negative values of n. N now is a region of convergence exterior to the pole. So this is now n greater than or equal to 0. And likewise, this n, the region of convergence relative to 2, it's interior to the 2, and things that are interior, the region of convergence when it's interior to a mode corresponds to anti-causal. So this region of convergence is interior to that pole, and that says then that this is going to be true for values of n that are less than 0. Is x of n stable? Let's say, is x of n a stable or bounded sequence? And there's a couple of ways that you can or think your way through that question, an answer to that question. What's one way? You could say, where's the unit circle relative to the region of convergence? Your region of convergence now is bounded inside by 1/4 and outside by 2. Where's your region of convergence? It's contained in that, the unit circle is contained in that region of convergence, which means what? It's bounded, isn't it, this waveform, even though it has a non-negative time sequence or a causal time sequence and a non-causal time sequence. Or you could, knowing the modes and knowing these powers of n and where they are defined, you could just sort of think your way through this, and this is 1/4 squared, 1/4 cubed, 1/4 to the 4th. Oh, that's collapsing. 2 to the minus 1, that's 1/2. 2 to the minus 2, oh, that's 1/4. Oh, that's collapsing. So you could have deduced the answer by looking at that information. So you've found the answer two different ways. Is x of n a stable bounded sequence? It's a stable sequence, or maybe I should just say stable, since the region of convergence contains the unit circle. Those 4 questions now that we've actually answered without doing any inverse C transform. But we now know what the inverse C transform better look like and its behavior. We first know that we need to split capital X of Z into 2 pieces in the result. Need to split capital X of Z into 2 pieces in order to give us the 2-sided time domain sequence X of n. We've already figured out that this mode 1/4 to the n is going to hold for non-negative values of n, and 2 to the n holds for negative values of n. And via the partial fraction expansion, we're going to find the contribution or the weights on those two modes. Our partial fraction expansion will now give us the specific value or expression for little x of n. And how do we do the partial fraction expansion for z transforms? What's the strategy? Slightly modified versus what you've done for the Laplace transform. Laplace, you just take capital X of s and you go. Now we have to divide this one by z so that when we solve for capital X of z, that z is explicitly in the numerator, since that's in most of our transforms in the tables. We need that z in the numerator. Meaning we now want to transform, or I'm sorry, find the partial fraction expansion of capital X of z over z. And if we were to go back and look at our capital X of z, it was z over z minus 1/4 as a factor in the denominator times z minus 2. And by dividing by z, we just have 1 over z minus 1/4 and z minus 2. We can now say, oh, that's a over z minus 1/4 plus b over z minus 2. And a we can find just like we've done for the Laplace. We multiply both sides through by the factor downstairs associated with a, which is z minus 1/4, and evaluate the left-hand side when that factor vanishes, or when z is equal to 1/4. So if we multiply that left-hand side by z minus 1/4, we end up with 1 over z minus 2. Evaluating at z equal to 1/4, we now have something a little bit, well, not sure I know how to word that properly, but it's now 1/4 minus 8/4, or 1 over minus 7/4, or a is now minus 4/7. And if you had your calculator, if you didn't trust your algebra, you could just do the expand function in on your 89 or your Inspire, and it would probably give that to you. It would give you this minus 4/7 and what this one's going to be, which is now 8 over 4 minus 1/4 in the denominator, or now 4/7. We now know that capital X of z is a times z over z minus 1/4 plus b times z over z minus 2. And remember, we had an annular region of convergence, so we really need to worry about these two modes corresponding to two different intervals or time regions, a non-negative region and a negative region. What is x sub 1 of n? Now we simply inverse z transform. We look in the z transform table, and this now looks like we have z over z minus r. That's just r to the n. And we know how it's scaled. It's scaled by minus 4/7. we now have minus 4/7 times the r, which is 1/4 to the n. And what do we know about that mode, 1/4 to the n? The region of convergence was exterior to that, so this was the causal piece. X sub 2 of n. And you might see this written many other different ways. If we, here's a real abusive notation, but you just, well, not an abusive notation. You just have to be awake and looking at the context or the contextual use of this expression. If I now used u of n to be the unit step, meaning this is 1 for n greater than or equal to 0 and 0 when the argument is negative. And that's, a lot of times we abuse that, and I now say u of n might be a generic input. So don't assume u of n is always the unit step. Is that clear? That's the overuse of u of n. I use it a lot of times to just mean some arbitrary time domain waveform, not necessarily the specific unit step. But if we use it here in this example, I could have written u of n, I'm sorry, x of n as minus 4/7, 1/4 to the n, and I'm going to switch it on for non-negative values of n. Meaning anytime n is non-negative, this will just be 1. And this now is going to be active when n is non-negative. And that's what I want. Is that clear? Plus 4/7, 2 to the n, u to what? Minus n. Now I want this guy to be on or switched on when the argument here is non-negative. Now I may have messed up at time 0. Yeah, at 0 this is not quite true, is it? But if we overlook that, then this would be a clean, and so I would have to adjust that for the value at time 0. So the cleaner way maybe to do it, so that's not quite right, is it? Does everybody see what's happening? This u would be on at 0, that u of minus n. And that would then give me this guy a 4/7 times 2 to the 0, which is 1. And I don't want that piece. So a cleaner way might be to just do it in 2 pieces. You might just say x of n is equal to minus 4/7, 1/4 to the n, and 4/7, 2 to the n for n less than 0. Is that okay? That one's a little better. That one's okay. That's x of n. Question? Yes, so the region of convergence I specified at the very beginning because I wanted to get a unique or obtain a unique little x of n. And if somebody gave you a different region of convergence, if they now said, oh, your region of convergence is exterior to 2, what do you know about little x of n? What's its structure? What's the structure of little x of n if both of these poles are inside the region of convergence? interior to the region of convergence, or the region of convergence is beyond those two poles. Pardon? Causal. Now we know little n is always going to be non-negative. The modes are still there. We have 1/4 to the n and 2 to the n. What's the bounded or unbounded behavior of little x of n in that particular case? Everybody get that? Now I have 1/4 to the n and 2 to the n, and n is non-negative. 2 squared, 2 cubed, 2 8. It's going unbounded, isn't it? Because the region of convergence did not contain the unit circle. It was beyond 2. The unit circle was not contained inside the region of convergence. Where were we at? So now if you change that, if you changed this, we want that to be on whenever this is positive, don't we? So now if n is 0, we don't want it to be on. So you were suggesting that putting a -1 in there. Now if we look at -1, we have what? What is our argument? If n is -1. Minus a -1, that's a +1, -1, so that's 0. That's okay, isn't it? And this guy is still off. This guy now, let's let n equal -2. Is this argument is remaining non-zero, or I'm sorry, non-negative, so it's on. So this now is a clean way to do that. So this is what we just did, right? We watched for when n was equal to 0, and this now will be sufficient to represent x of n in one line. Now, what we want to do is start talking about how do we convert systems from continuous time to discrete time, and that's where we'll pick up after the exam, or a week from today. Thank you for your patience, because I ran over a couple minutes.